2021 conference for the first keynote. My name is Achille Patavina, Politecnico di Milano, and it is my great pleasure to introduce Professor Jafar El Mirghani, University of Leeds, UK, who will deliver the keynote entitled Energy Efficiency Everywhere, Cloud, Fog, Virtualization, RAN, and IoT. A few notes about the outstanding career of my friend Jafar. Professor Jafar El Mirghani is Fellow of IEEE, Fellow of IET, and Fellow of Institute of Physics and Director of the Institute of Communication and Power Networks in Leeds. He has provided outstanding leadership in a number of large research projects, secured over £30 million in grants, and was PI of the £6 million EPSRC Intelligent Energy Aware Networks program grant since 2010 up to 2016. He was PI of the KISS Era Star project with a focus on energy efficiency. He is co-chair of IEEE Sustainable ICT Initiative, a pan-IEEE society initiative responsible for green ICT across IEEE. He was awarded many times in international competitions. His work led to 5 IEEE standards with focus on cloud and fog computing and energy efficiency. He is area editor of IEEE JSAC series on machine learning for communication and is currently PI of the EPSRC 6.6 million pounds terabit bidirectional multi-user optical wireless systems for 6G. He has published over 500 technical papers and has research interest in energy efficiency, as you can imagine, optimization, machine learning, cloud, and fog computing. Jafar, the floor is yours.
Thank you. Thank you so much, Shakili, for this very kind introduction and also invitation. I'll try to share my screen, and I hope I can get that working fine. Okay. I hope you're able to see my screen now.
Yes.
Okay, good. The slide should just come momentarily. Okay, so thank you so much for coming to this talk. As mentioned by Achille, it's entitled Energy Efficiency Everywhere, Cloud, Fog, Virtualization, RAN, and IoT. I'm Jafar El Mirghani from University of Leeds, and this work was sponsored by EPSRC and also in collaboration with the IEEE Sustainable ICT Initiative. So this is an outline of the talk. I'll start with an introduction. I'll talk about energy efficiency drivers. And as you can tell from the title, I included quite a number of areas here. And one of the key reasons for doing that is to give a bit of exposure, a bit of a wider exposure for what is to come in these areas, but also energy efficiency by its own nature. Usually people make their own bit more energy efficient and they push the problems elsewhere. And therefore it is very important to look at the end-to-end picture. In terms of reliability, it is very important for networks to be energy efficient. Otherwise, we will not be able to find the energy sources needed. So I'm going to talk about wireless and access networks. I'm going to talk about IoT networks, core networks, data center networks. I'll outline some of the testbed implementations we have done and some future directions. So in terms of energy efficiency itself, this is a diagram that was produced by the Lawrence Livermore National Laboratory in the US, and it shows power consumption in the US. So this is in 2019. On the left here are the different sources of energy, so going all the way from solar to nuclear, hydro, wind, geothermal, natural gas, coal, biomass, and petroleum. The thickness of the line here indicates how much energy is drawn from that particular source and used currently. And here are 4 very broad categories in which we use energy. So residential, commercial, industrial, and transportation. So a very thick line coming here out of petroleum going into transportation means we use a lot of the petroleum energy for transportation. A bit of it is used in industrial, a bit of it, very small amount in commercial, and very small in residential. potential. If you look at many of those sources of energy, they go to produce electricity, and this part here is the useful part that gets converted. So this is all the input energy. This is the useful part that gets converted to electricity, and this is how much is wasted. And if we look at the energy that we waste all over the world versus how much we use, we waste about 2/3 of the energy, potential energy that we have, and we only use about 1/3. And therefore, there is a very strong need for energy efficiency. Looking at it in our own area, the ICT area, we know that, and probably you have heard already that when flights or aircrafts used to fly, ICT and the internet had a carbon footprint that is comparable to the global aviation industry. This ICT, and unlike aviation, is obviously growing very fast. So it is broken down into 3 main areas. This is from the GESI Smarter 2030 report. About 47% of the carbon footprint or the energy use roughly is due to end user devices, about 28% due to data centers, and about 24% due to networks. So in this talk, I'm going to focus on the data centers and the networks, those 2 elements. I'll not be touching on the end user devices, although those are also very important. Now, if we look at the traffic in the internet, and this was produced by Bell Labs and part of Green Touch, we had traffic growing in the internet at 300%, and that was just before the turn of the century. People expected it to grow even more. Instead, this is what happened, and therefore we had the burst of the bubble around about 2000. But if we look currently, the traffic is still growing at 30 to 40% per year, which is very significant. And if we have growth at 40% per year, that means traffic doubles every 2 years, increases by a factor of 30 in 10 years, and by a factor of 1,000 in 20 years. And therefore, that roughly around the year 2010 produced the 1000x challenge, which was a very important challenge that the community was given to try to find ways to improve energy efficiency in all the network and data centers and so on. Because if we're able to improve it by a factor of 1,000, then in 20 years, we will be able to accommodate the traffic growth, means 1000x more traffic, but still consume the same amount of energy as we do today. And if we look at a breakdown of what this means for the network, so this is the year versus the traffic in terabit per second, a North American example in this case. The smallest by volume and the slowest growing is wireless voice. The fastest growing is wireless data. The largest by volume is internet video, and this is followed by peer-to-peer. Again, this is some set of diagrams from Bell Labs. So if you wanted to do something, those would be the 3 areas where you need to address power consumption in wireless, in video, and so on. And hopefully I'll give you a flavor of what can be done in these individual areas. So Green Touch, Nakili knows about this quite well, since we're participants in this, produced a number of white papers that looked at how power consumption can be reduced, and did lots of challenges, and showed how this factor of 1000 can be achieved. So I'll give you just an idea about one part of the network, which is the core part of the network, where we did quite a bit of work, and how it achieved its gains. So the gains that were required in this part of the network were a bit less than 300, maybe about of the order of 100 or something like that. But what was achieved was about 315x improvement in energy efficiency. So in 2010, we had energy usage. Remember, this is in fiber, so we're not talking about microwatts. We're talking about not microjoules. We're talking about nanojoules. So about 360 nanojoules per bit, and in 2020, about 1.1 nanojoules per bit. How was this 300x achieved? It was not achieved through improvement in just one area, but a combination of areas. So we have more slow and growth or business as usual, reducing power consumption in devices and integrated circuits and so on. And over that 10-year period between 2010 and 2020, that was about 4.2x. GreenTouch introduced a number of innovations into the equipment that helped reduce power consumption. So, for example, optical interconnects, when you look inside routers and so on, a lot of the power is used in interconnecting different parts of the router, and these many times are electrical interconnects. Optimized packet processing. So as we move into IoT and machines and things like that, we will end up having more and more smaller packets. And therefore, if you have these big headers at the front, that can result in a lot of power consumption. You have lots of small packets coming all the time. And therefore, you can look at increasing the clock speeds and reducing them according to what you have to handle. Optimizing the signal processing in transponders. So those produce about 4.7x. Deployment and management of protection equipment. So up to 2010, a lot of the protection equipment in the different operator networks were left on all the time. This is when you wanted to do real-time kind of protection. And being able to find algorithms and so on to deal with that can result in about 1.9 or almost a factor of 2 reduction in power consumption. The optical layer is a lot more efficient than the electronic layer. So if you bypass the electronic layer, you get a factor of 2. Dynamically allocating line rates. Usually, if you look at networks, there is a lot of wastage. So you may have a very high data rate or transponder at 100 gigabit, and you're using a small part of it. And therefore, adapting can help. Optimizing the network topology and also virtualization, meaning trying to consolidate and help put things together to make the best use of the available space. That can help instead of having dedicated equipment everywhere that is underutilized. So you can consolidate somewhere at the edge of the network or the center of the network. So hopefully this gives you an idea or a bigger picture of where we can get this. So this is the core part of the network and part of the virtualization and data centers and what they achieved. The wireless had to do its part, and the access network also had to do its part. So within this project that Akili mentioned, the Intelligent Energy Aware Networks Internet Program Grant, we looked at a number of different areas. How can you use renewable energy in a network in the most efficient way, whether it is solar or wind? Some of the challenges there are to deal with the fact that we usually design those networks with the assumption that the power supply is reliable. Power supplies are not reliable, and therefore this is an area where a conference like this and people in this area would have a lot of interest trying to model these renewable energy sources as stochastic processes. So this may be a Weibull distribution for wind, for example. And yesterday there was a tutorial on stochastic optimization and I guess robust optimization and so on. And there are many things you can deal with here. So essentially, when the sun does not shine or the wind slows down, etc., you can think of this as a failure in your network, and you have to deal with it. Or maybe plan it or react to it, etc. Then topology optimization, the network itself has to be optimized. So we produce some of the early proofs that if the traffic is very symmetric, then the best thing you can do is to have a full mesh. And if it is traffic symmetric, means everybody wants to talk to everybody at the same rate. If the traffic is very asymmetric, that means there is a dominant node like a data center, then one of the best topologies is a star topology. We looked at content distribution. How can you construct different clouds in the center and the edge of the network in a way and route data in a way that minimizes power consumption? Content caching, you may have content videos somewhere in the center of the network, and you go down IP layer, optical layer, IP layer, and you go to the server. I mean, Leeds, London is maybe 300 kilometers, 300 miles away, and the server may be there, and I go and consume all this energy there. Alternatively, I can have a local cache locally here, and I consume things locally. Now, this adds a piece of equipment, but overall we win. Why do we win? We win because content is not all equally popular. So if you look at YouTube, it may have 500 million videos, but only maybe the top 100 videos will account for 80% of the hits. So if I was to cache them here, I can win. Big data networks, I'm going to talk about those, and machine learning and so on a little bit more, and vehicular networks as well. So I'm going to go through use cases, and I'll just give you a flavor of each area and how we did that. Now, the tools, I'm not going to go into the mathematics and so on of what is done here, but suffice to say that many of these are about optimum use of resources. So you can think of in each of these areas an optimization process being formulated, either solved as a mixed integer linear programming kind of problem, or alternatively, it may be a stochastic optimization if you have some form of randomness. And in some cases, like this here, also use machine learning. So big data analytics for wireless networks. So the idea here is that we have a network, and this network is instrumented, meaning we measure many of the entities in this network. We send the measurements to a big data cluster somewhere, either in the network or at the edge of the network or central to the network. Here we run different machine learning algorithms. And we try to, with different objectives. The objectives in this case may be to reduce power consumption, or can be Pareto, like you have multiple objectives. So reduce power consumption, and in this case also give priority to a certain set of users. Then you make a decision and you try to apply that to the network to configure it in the best way. As I go along, I hope those slides will be shared. So there are some papers here that give you further information about each of the areas. So in this case, in addition to reducing power consumption, we try to prioritize some users, and those are, it is a healthcare application. So those are users that require attention. And in this case, we selected stroke patients. One of the reasons we selected this, as you know, one of the kind of usual issues with machine learning is that you require some reliable, real, as opposed to synthetic data sets. To be able to get to some useful results, representative results. So there was an ongoing study that started in 1948 in the US, in Massachusetts, that looked at a number of adults, about 5,000 or so adults, and followed them over the generations. Obviously, as people pass on, so there will be others. So it is now in the third generation. It did a lot of measurements, so we have access to things like cholesterol level, blood pressure, smoking rate, and so on. And you can think of those as a feature set in your input. And the idea is that you would use those features and some knowledge of the patient history to give them a priority in the network, so that you can tell first if they are high risk or not. If they are high risk, you give them priority in the network. If they need attention, then you would send messages to get an ambulance or something like that. At the same time, we would want to distribute the resources in the network in a way that minimizes power consumption in that network. So you can think of it this way. So there are a number of IoT devices attached to the user that goes into this kind of machine learning set of algorithms that have got multiple objectives. Some of the objectives are to prioritize those users. In addition, you get the health record of the user, because you cannot just base it on the instantaneous measurements that you're seeing now. At the same time, you may get measurements of the network and also some history of the network. And in this case, you produce priorities for the patients and try to allocate them resources. One of the reasons, of course, you can have for multiple illnesses as well. In this case, it is stroke, but you can have things for heart conditions and so on. Strokes were quite important, talking to our medical colleagues, because they are very silent, so people don't see them coming. I guess others are the same way, but essentially the same framework can be used or applied in these cases. And in addition, you can look at different kind of metrics. In this case, it was maximizing a weighted sum rate. So here you would allocate resources to the different users, and it may be heterogeneous with big macrocells and microcells and so on. So you may want to maximize a weighted sum rate, and in this case also here we did a fairness or prioritizing outpatients. So we have got 10 users, 7 of these users are normal people and 3 are patients. And the idea, if you can let them out into the go back home, you would release the pressure on your hospitals, etc. But at the same time, be able to monitor them reliably. And reliability here is very important, because if your system cannot provide the guarantees, then people will want to stay, and doctors will want them to stay in the hospitals. If you can provide the guarantees and the reliability, then this may be a way that is economically also very good, and for the patients to be in their own home environment. I'll go on to talk about a second case study, and this is about virtual machine placement and migration. So here we have an end-to-end network that is composed of a core network, is composed also of a metro network, and then there is a form of access network, and then the end users here. This was implemented in a countrywide, or I guess it is more of a continent-wide setting in the US here. This is the AT&T network, for those probably familiar with that kind of topology. The processing can be done in three main sets of locations. So in the core of the network, I'm showing only one, but obviously you can have in each city, you can have one of these big data centers, or few in the whole country. And then in the metro, so we have metro fog, and then we have access fog, and this would be only maybe of the order of 3-5 kilometers maybe from the user. We know now also people want to have fog in the building and so on. And the idea is that you have a set of virtual machines that may want to cooperate with each other, or may want to synchronize. So you update one of them and the others get updated, or they may collaborate with one another to solve a given problem. The question is, where should we place the processing? If you place it somewhere central here in the network, then you get to make use of the consolidation effect, meaning many users can share the same resource coming from different points of the access network, etc., and you save maybe in your processing capability. But then you have to go up and down the network, and this consumes more power, but also induces more latency and adds traffic in the metro and the core of the network. Now, as you can imagine, then a possible solution is to migrate and do the processing towards the edge of the network, which is good in that you reduce the latency, you reduce the traffic, but you add more components in the network, which can consume more power. And therefore, there is that kind of trade-off. And one of the important aspects to look at is how good is your computing hardware in terms of power consumption versus load. So usually we have an idle power, and then after that, the power consumption increases with load. So to give you an example, a computing machine that is not so good may consume a maximum power of 300 watts, but the idle power is 250 watts. So as soon as you switch it on, it consumes 250 watts. And regardless of how much you put into it, it does not increase a lot. And this is not a very efficient machine to try to distribute around. Now, so here are a set of results. At one end, we have the exact opposite of what I described, which is a kind of machine where the power consumption increases almost linearly with the load that you put there. And the question is, can we do that? And there is a standard now in IEEE that looks at this, and hopefully I'll quote it towards the end of this presentation. If you have that, then depending on the data rate at which you are communicating between the user to the entity to be processed, generally it tends to be a very good idea from an energy efficiency point of view if you have these very proportional computing load and power consumption are proportional to each other. It's very good to distribute and bring things very close to the edge of the network. Except when the data rate is very small. So if the data rate is very small, it turns out in this particular example that it may be also useful to consolidate somewhere in the center of the network. At the other end, where as soon as you switch it on, it is 250 watt. By the time you put full load, it just increases to 300 watt. It is better to kind of consolidate from an energy efficiency point of view, because many of these will be partially loaded in the access, because we know that is the nature of the access. And therefore, all these idles of 250 watt hurt you a lot, and therefore it is better to consolidate somewhere here. And there are some papers that discuss this in a lot more detail. I'll move on to a third use case, which is wireless network virtualization and energy efficiency. So you can think of the usual wireless network where now the end points are reduced to a remote radio head that has got very little intelligence, just the RF part. There is an optical network and passive optical network with ONUs, optical network units near the cell tower. There is an OLT, an optical line terminal, which is in the telecom office, maybe 3, 5, 10 kilometers. Deep reach phones can do up to 100 kilometers, but usually these are in the center of a city, therefore about 5 kilometers or so. And this is the core network, and maybe one of the core nodes is in the city that you have. And the idea here is you would separate the different functions, and I know 4G calls them something and 5G calls them something else, but roughly they increase in the kind of data rate that you need to have between your remote radio head and each of those entities. And those are virtual network functions. So you have your baseband processing unit, and this will have a lot of data rate between it and the remote radio head. And therefore, if you are virtualizing and you're trying to put it somewhere, to push it all the way to the... Akili, can you hear me still okay?
I can hear you. We had just a short interruption, but now it's okay.
Akili, I cannot hear you. Are you on mute?
No, I'm not on mute.
Jafar, can you hear me? Jafar?
Jafar has a problem.
Is it okay? Yeah.
We hear you.
Okay, I'll continue.
Okay.
Yeah, if you can please repeat.
So you have your baseband processing unit, and you would want to place them somewhere close to the remote radio heads. And then because of the very high data rate, so you would want to place them maybe the ONU or the OLT. Then you have things that are much slower changing, like the mobility management.
It's gone. He's gone.
We lost Jafar.
Yeah.
This is 5G.
Yeah, we don't know which part of the network is failing now. Maybe the core. We have to wait that he joins again the chat.
Here he is. Hello, Jafar.
Yeah, hello, Akili. I'm not so sure what happened. Did you lose me somewhere during the talk?
Yes, we lose you in the case study of wireless. Use case 3.
Okay.
You were describing the virtual platforms.
Okay, fine. I will try to go back to that. My sincere apologies.
No, it's not your fault. It's okay.
Yeah, sorry about this. Okay, let me just go. I think I was on this slide.
Yes.
Okay. So I will just put it into presentation mode. So hopefully it will come soon now. So Akili, can you see my slides okay?
Yes, it's okay.
Okay, good. So I mentioned that we have got a number of virtual network functions, and we want to place them in a way that minimizes power consumption. So we have some that involve a lot of traffic, like the baseband processing unit, and those you have to try to place very close to the remote radio head. Some that are very slow changing, like the mobility management entity, you may want to place them a little bit back, because then they see the whole network and they can do better better handovers and things like that between the different cells. And then you have home subscriber services, policy control rule functions, also slower changing. The gateways, the packet and the switching gateways may also need to be a bit closer. And if you virtualize compared to no virtualization, so with virtualization, you save quite a bit of energy by being able to consolidate resources and use them in a better way. If you add content caching, in this case here we have a number of content caches, then compared to the case where we just do virtualization on its own, if we were to do content caching as well, then we save even more power consumption. So I'll move on to use case number 4. Sorry to keep checking. Akili, everything is fine?
Yes.
Okay, good. So this is an IoT service embedding example. In this case here, what we have is we have a number of a smart city application. We want to compose services, IoT services, in a way that minimizes power consumption. And the entities that we have at our disposal to compose services are usually processing entities, some form of sensors, IoT sensors, some form of actuators, and then the network. So the idea is that we use them to compose a given service for a given amount of time and do it in an energy efficient way. And afterwards, we decompose or release those entities so that they can be used by another service. So a security service, for example, may employ sensors, maybe some motion detectors, some RFID. As actuators, it may employ display screens and maybe some alarms, and also the network and processing. And you may want to deploy this security service because you have a match happening somewhere in the city. Therefore, you want that. An energy saving service may have, again, motion detectors, temperature sensors to save energy in building, fire protection, maybe some temperature sensors, smoke detectors, etc. So the idea here is you would want to compose and decompose this network in an energy efficient way and use the resources in the best way. So there are some papers here that give a bit more detail. Here we compare different, so each of those services we refer to as a business process. And here we have 2 business processes, up to 12 different business processes. These are services. This is a case where you compose them just to minimize cost. And these other ones, so here to minimize cost, and these are the ones where you do it with energy efficiency, reprovisioning, and sequential. And there is quite a lot of energy that can be saved by optimizing that problem and looking at the network power consumption and the processing power consumption. I'll talk about joint core network and cloud virtualization. So here we have a network, a substrate network, a physical network, and we have some virtual network requests that have to be embedded here. And the idea, we want to embed them in a way that minimizes power consumption. Many times people solve this problem, this embedding problem, to minimize the cost of the network. And as you can see, there would be many different ways in which you can choose to do this embedding, the transformation from the virtual to the substrate network. This is one particular option, but this may not be the most energy efficient way of doing it. So you need to look at the exact set of equipment. Here in this case, we have an optical layer, we have an IP layer, and in addition, we have in each of the nodes. So each of those nodes not only represent communication equipment, meaning optical switches, routers, etc., transponders and all that, but also some processing equipment. And we want to slice all of those and provide them in a way that improves energy efficiency and realizes these different virtual network topologies. Here are comparisons between what you can do if you were to just minimize the cost. So for example, some of the curves here minimize the cost. And if you were to do it with energy awareness or with energy efficiency, the improvement in energy efficiency or reduction in power consumption is about 60% maximum, 20% average. And what we did here is we tried to put all the requirements into the algorithms to try to find the best way to configure this network. Many times people think that the best way to save energy is to turn things off. And that turns out to be a very bad strategy. Not very bad, but not the optimum strategy. Because many times if you turn things off, what you do is you end up creating longer routes to get to the next set of resources that you need. And that can waste a lot of power. So the best thing to do is if you want to minimize power consumption, tell your optimization minimize power. Don't put into it your own thinking that turning things off is a good idea. Don't do that. Just ask it to minimize power consumption. And by doing that, as opposed to the guy who says turn off things because that saves power, we are about 9% better. And it is just a point to note that it is better to give it freedom to choose the optimum. Here is another example about virtual machine placement. So we have a network, we have a number of users, and those users are interested, number of users who are interested in a number of virtual machines. They want to access those virtual machines. The question is, where should we build clouds and where should we put the different virtual machines? And then how do we route the traffic in an optimum way? It turns out that there are three different things we can do. We can migrate virtual machines, we can replicate them, or we can slice them. So imagine if there are users somewhere here that are using virtual machines and connecting, so in the east coast of the network and connecting to the west coast of the network, then maybe we can migrate the virtual machine to the east coast and we can save power. At the same time, if you migrate it, there may also be people here who want to use it, and that is not very good. So you think of replicating it, making 2 copies. And in the end, making 2 copies can either double the power consumption or can just increase the power consumption in proportion to the load. If it doubles the power consumption, we call it replicate. If it increases the power consumption in proportion to the load, we call it slicing. And if you slice, then you save way more power, about 27% in this case. And if you slice, the answer is to put virtual machines everywhere. If you migrate or you choose the migrate or replicate, then the best thing is to place the virtual machine somewhere central in the network. I'll cover a use case here where we do something similar but with video. So here are a number of users who are interested in some content, and the question is, where do we place this content in the network and how do we do the routing in an optimum way, given that the content has got ZIF distribution for its popularity. As you can tell, if content is, so the important parameters here are several, but 2 are very important. One is the amount of traffic you have in the network. So if everybody is sleeping, there is no point in making copies of content and placing them everywhere because no one is going to be using them. So if the traffic is very low, like 6 a.m. in the morning, the best thing you can do is just put your content for all popularity groups. So the rows here are how popular the content is. Near the top is the most popular. The columns are the nodes of the network. So if it is 6 a.m. and everybody is sleeping, just put all your content or switch the service at the center of the network so that they serve everybody, and that minimizes power consumption. If it's about 10 p.m. and people are watching and things like that, then put the very popular content everywhere, and the least popular content, keep it in the center of the network, and that saves power. And in this case, we get a total saving of 40%. We save 70% or so in the network because you're bringing content closer to the users. Another example here is big data networks. So in big data networks, what we have is we have maybe healthcare applications, we have financial institutions, social media, and so on, sending a huge amount of data to be processed in central data centers. But essentially, this is data and not knowledge. Many times we're interested in the knowledge embedded in the data, but not the data itself. So you can think of an example where you have a heart rate monitor. So if you send the whole waveform to be processed in the data center, then hopefully for the next 20, 30 years, this will be saying the person is fine, fine, fine. So there was no point in sending that very big file to be processed in the central data center. What you could have done is to try to process it at the edge of the network here. So we started with big chunks, 3 of them. We were able to process 1, and that is info. We call it info. We come to the next node, and the 2 that were not processed are now processed, and we extract the info out of them. So in essence, we are interested in the knowledge and not the data. And that is a very important distinction, because once the person needs help, then we send a message to the doctor, we send a message to an ambulance to come to them, and that info tends to be much smaller than the waveform itself. And you can save, in this case, up to 70% or so power consumption. This is the last use case that I'm going to go through, and it's about data center disaggregation and virtualization. So he would know that many companies now are pursuing this idea of disaggregation. So currently a server is a box that contains your CPU, contains your memory, contains your NIC network interface card, your input-output, and is very rigid in that. So virtualization helped, but people also now realize that the box itself is very rigid in that you imagine you have got an application that requires a lot of input-output, so very high traffic, but very little processing. So the CPU will be sat inside the box doing nothing, but you cannot get to it because the I/O card, the input-output card, is fully occupied, and therefore that is processing capacity that is wasted. And at the same time, you may send few kilobytes of code that is very hard to solve, and the CPU becomes fully engaged, and the I/O card is sat doing nothing. So the idea here is that you would compose on the fly a further stage in virtualization, compose on the fly a server of the size you want. So maybe the server that you want for this particular job should have 3 CPUs, should have 1 card, input-output card, and should have a given amount of memory. So you try to have racks that are monolithic. So one rack that only contains input-output devices, one rack that contains CPU only, and one rack that contains memory only. And you connect them through an optical network, and you compose the server you want for the duration you want virtually, and use it, and then disintegrate it, and that produces a lot of efficiency and energy as well. Here are some more papers about this. And
5 minutes left. We should leave some small time to questions, maybe.
Okay, I will try to finish within the next maybe couple of minutes. Thanks, Achilles. So the best energy saving we get in this case is 63%. I'll talk about testbed implementation. So this is the kind of set of testbeds we have in our lab. There are a number of edge processing units. In this case, there is video that gets injected into one. So those are servers. So 3 servers here represent 1 edge processing unit. So video gets injected here, may go to further edge processing, then goes through a fiber, goes through 3 core nodes. So these are WDM nodes, 400 kilometers of fiber, and comes at the other end and gets processed here, and then goes to the end user. And we implement many of the algorithms in NetFPGAs, which are a network card with an FPGA for implementing your algorithms. So you can think of a network like this, so remote radio heads or an edge or IoT edge processing core network, and then you come at the other end and you do processing, and you can also then move processing from one location to the other. So this is the overall kind of view of the network. You have many entities or points at which you can do edge processing. It is an IP over WDM with a PON with cloud and fog at the edges attached. I'll just say 1 or 2 words about the IEEE Sustainable ICT Initiative. So this is an initiative whose goals throughout IEEE to reduce power consumption and promote sustainability. It produced 9 standards. It also produced the new IEEE transactions on green communications and networking, which started in 2017. And we're setting up now a new magazine, an IEEE magazine, Sustainability and ICT. This is a call for participation, so please come and join us if you're interested in this area. Those are the 9 standards, 1922.1 to 1929.1. The work that I have just described talks about standards from 1925.1 to 1929.1. So these are the dynamic line rate, the big data I talked about, the virtualization, moving virtual machines, and content distribution. And finally, future directions. I think there are many areas. So life cycle optimization of networks to reduce their carbon footprint. Many times people only think about operational energy, the energy used to operate the network. You should also think about embodied energy, the energy you use to manufacture the equipment, and disposal energy, the energy you use to dispose of your equipment. So when you form your optimization cost function, please don't only put operational energy, put those others as well. Intelligence everywhere, machine learning and AI to improve energy efficiency. efficiency. They are also using a lot of energy themselves, those machine learning and AI algorithms, so we need to look at ways to improve them. Interplay of resilience and energy efficiency. One requires redundancy, the other talks about efficiency, and therefore there can be many stochastic settings where this can be useful. And reliability of the unreliable edge. The edge is always kind of thought of as being unreliable, and therefore trying to introduce reliability into it. I'll stop here. I hope the slides are going to be shared, and therefore there are a number of papers there that hopefully you can look at in a bit more detail. And thank you so much, Akili. If there are questions, I'll be very happy to answer those.
Yeah, thanks a lot, Jafar. Very interesting presentation. The presentation will be made available to attendees. Just a remark, the file that you just sent me is different from the one that you showed, because my file contains 7 use cases. So it seems you have an updated version that if you send us, we will make it available as a PDF to attendees.
Yes, I'll send it right.
Okay, let me ask the attendees if they have any questions to Jafar. We have just a couple of minutes, one quick question at least.
I have one.
Okay, go ahead.
First of all, thank you very much, Jafar, for accepting the invitation and providing this very interesting keynote speech.
Thank you.
When you talked about virtualization and placement of virtual machines, in particular in the, I think in use case 3 and 4, I was wondering if you took into account also the movement of people and distribution of population during the day in urban area or the area where you, and if you think that moving the virtual machines to follow this movement is possible and convenient.
Yes, it's a very interesting point. Thank you so much for this question. We did 2 kind of approaches. So the short answer is yes, we consider that, because part of the picture is you would consider to start with population in the different cities, because that would be a kind of an indicator of the amount of demand. And then here, I think this is what you're asking about, people moving even between those kind of edge points where maybe the radius around each of them is 500 meters. So while doing the kind of mixed integer linear programming optimization, we took snapshots. So you would see a snapshot where the users are here, a bit later the users have moved there, and so on. In the more online algorithms, we try to look at this kind of handover between the two. But in general, the way we try to do it is we have the virtual machines ready, but we just kind of activate them when you want to move workloads. But it is an important area, I agree, and it is also probably one that is not very highly investigated, because usually virtual machines are placed somewhere in the center of the network, and therefore if users move, that doesn't require a lot because they just move the communication path, as opposed to here having to move the virtual machine itself.
Thank you.
Thank you.
Is there any other question?
I think there is one question.
From whom?
Let me
Yes,
see.
hello, I'm Jacek Rak from Poland. May I ask one question?
Yes, go ahead, Jacek.
Yes, so just a short question. Jafar, thank you very much for a very interesting presentation. I wonder if your results, if you have any comment about the observed characteristics of traffic due to pandemic. As we can see, traffic becomes more symmetric. At least uplink transmission is greater than before. So do you think your results might be impacted by this change by much, or?
Yes, it is. It is very, very interesting. I think The short answer is we have not run any kind of new results looking at symmetric traffic, uplink versus downlink. But in the very initial kind of studies that we did in GreenTouch, that was a requirement. So we looked at, they were hypothetical. Obviously, this was some time ago, so we did not know about any of this. But the idea was to try to look at things that are very symmetric, meaning every user wants to send to every user at the same rate, etc., versus the very asymmetric or the end of asymmetry where there is one dominant user, like either an edge processing node or a big data center, and then how the network design, the protocols, and so on can be changed between the two. So in that sense, we looked at it, but not in the practical sense of what has happened more recently. But I think it is, yeah, it is very interesting to look at that.
Okay, thank you.
Thank you. It is a very interesting point, how pandemic is changing things in our society. Very interesting. So we are 4 minutes late. I think it's time to close this session. Thanks again to our first keynote speaker, and I leave the floor to the next session. I think Giacomo will be session chair.
Just a small technical interruption. When Jafar will send us the final slide set, we will post it on the website, the same link where you can download the proceedings, and the same we are doing for yesterday tutorial material from Michel. So you will find both there. Thank you.
Okay, Guido, can you please promote me to okay, thank you. Okay, so welcome to session number 2 of DRCN 2021, and the topic of this session is software-defined networking. We are running very few minutes late, so I hope you will enjoy this session, and we will show the videos, and then there will be some time for some questions from the audience. I would like to ask all the speakers to please raise their hands so that we can promote them. Okay, so the first speech of this session is improved routing in networks through load prediction strategy, and we have here Ron Posty from Ben Gurion University of the Negev, Israel. I have a video, so I will show the video, then Ron will answer your questions.
Ma è solo a me che appaiono quelle cose senza.
Hello everyone, my name is Ron Posty from Ben Gurion University. Today I will talk about my thesis work, which is improved routing in networks through load prediction strategy. My work is supervised by Professor Michael Segal, a full professor in Ben Gurion University. So we'll start by introducing the background and motivation for this work, include the problem definition. Then I will briefly describe the theoretical proofs for this problem, followed by results that justify the presented lower bounds. Then, of course, the conclusion of this work. So today, most of the networks are characterized as multi-routed trees, which means that there are more than one shortest path between the network elements. And the calculation of the shortest path is made by routing protocols, which runs locally at each node. And there are a new paradigm called software-defined networking, which aim to decouple the control and data plane, such that it allows us to centralize the control plane and using centralized routing algorithms with the global network knowledge. And so as mentioned, there are more than one shortest path between a pair of network elements. And in order to utilize the network resources, routing algorithm tries to split their flows across those equal paths to balance the load over the available shortest path. The most common load balancing method called ECMP, equal cost multipath, which makes static hash on packet headers. And this method could possibly cause to overloading of congested links. For example, while routes the same big flow through the same congested link, while other links are underutilized. So to define the problem statement, we first define two main parameters for our work. The first parameter is a flow network, which is a network with a node, edge, and edge capacity that calculates the number of packets that consist in each edge for a given timestamp. And the second parameter is the load prediction algorithm, which with prediction accuracy of P. And note that LPL load prediction algorithm is calculated for each timestamp, and its results is a list of network loads. So the problem is given a flow network G, we should find the P threshold in which the efficiency of LPA is better compared to ECMP. So our first proof is a focus on the existence of load prediction accuracy lower bound in Fetri topology. In Fetri topology, the performance of routing decision based on a load prediction algorithm is not worse than that of ECMP when the prediction accuracy is greater than k minus 2 divided by k, which means that the k minus 2 divided by k is the lower bound for Fetri topology. In this case, we assume that the collision occurs when two flows are routed through the same congested edge at the same time if they surpass the edge capacity. So to find the lower bound, we'll calculate the probability for collision using ECMP and compare it to collision probability using a load prediction method. Using ECMP, the probability that two flows collide at a specific edge is the probability that one flow routes through an edge times the probability that the other flow routes through the same edge. For Fetri topology, with k pods, this probability is 2 divided by k in power of 2, where in this equation, sigma st is the number of shortest path between S and T, source to a target, and sigma st of L is the number of shortest path between S and T that route through edge L. In contrast, with prediction accuracy of P, the probability that those two flows collide at this specific edge is when the load prediction algorithm won't tries, which in our case is 1 minus P in power of 2. So to calculate the lower bound, we should find when the probability of collision with ECMP is greater than the probability of collision with load prediction algorithm, which in our case is when P is greater than k minus 2 divided by k, which is our lower bound from the theorem statement. Our second proof shows the existence of the load prediction accuracy lower bound in symmetric dragonfly topology, where symmetric dragonfly is a dragonfly topology with A, which is the number of nodes within each group, equal to H, which is the number of links that connects each group to all other groups. So in a symmetric dragonfly topology, the performance of routing decision based on load prediction algorithm is always not worse than ECMP when the prediction accuracy is greater than 50%. And this proof we generalize the scenario of n interflows, or in other words, a collision scenario of n flows between groups. Okay, let's start. So we define a general topology as follows: given an SDF with m groups, we define n flows such that G1 contains the specific destination node, which means that there are a possibility that m is less than n minus 1, which means that at least one source is a multiple flows to G1's destination. A possibility that m is equal to n minus 1, where at most for each group has exactly one flow to G1's destination, and the possibility that m is greater than n, where there are at least m minus n minus 1 groups without flow to G1's destination. So let's calculate the probability that at least two flows will collide. This probability is equal to the complementary event of the probability that one flow or none of the flows route through this edge. The probability that one flow will route through this edge is to choose one of n flows, which is 1 of n, times the probability it routes through this edge, which in ECMP is half, 50%, times the probability that the other is not routed through this edge, which in ECMP it's half in power of n minus 1, which in case of ECMP, this is the probability. So this equation shows us the probability for collision in case of using ECMP. For load prediction algorithm-based routing, the probability that at least two flows will collide using complementary event, the same calculation, but using the p parameter, the accuracy, and this is the equation. So now we can calculate the lower bound as we calculated before for fetch topology. And by using Wolfram alpha, we plot this in equation. And by the assumption boundaries where p is less or equal to 1, and n, the number of flows, is greater or equal to 1 also, this equation is true as long as p is greater than 0.5. Which means that as long as the accuracy is greater than 50%. So as long as the prediction accuracy is greater than 50%, load prediction-based routing is better than ECMP. It is an interesting fact or proof because for FET-tree, the lower bound depends on the FET-tree parameter k and the topology size. And for a symmetric dragonfly, the lower bound is a constant number and does not depend in any topology parameter. So our simulation, the simulation was written on a Python using well-known libraries together with self-developed package. At first, the simulation built the network topology according to its parameters. Then the simulation ran standard ECMP. While during running ECMP, the simulation captures some network data like the arrival the flows and the edge load for each timestamp. Using those capture, we could perform a simulation with mutable prediction accuracy in order to show the correctness of the proven lower bounds. Finally, we examined the correctness of the proven lower bounds by looking at the packet loss index. So for FET-tree topology, we ran a simulation with k equal to 8, which means that the lower bound should be 75%. As you can see in our figure, the plus line presents the ECMP running simulation, with the dashed line presents the prediction simulation with different accuracy, such that as long as the accuracy is equal to the lower bound, the prediction and the ECMP simulation are almost the same, as you can see here. Okay, the plus line and the dash red line. ECMP simulation are almost the same as when the prediction accuracy is greater than the lower bound, and the number of packet loss decreasing. Okay, as we can see here, as long as the accuracy parameter p is less than the lower bound, the packet loss is greater than the packet loss when using ECMP, and as long as the prediction accuracy is greater than 75%, the number of packet loss is decreasing. And for SDF, symmetric dragonfly topology with 8 group and 8 nodes for each 8 nodes for each. We can see that the lower bound exists and it's exactly 50%. Here you can see that as long as the prediction accuracy is less than 50%, there are more packet loss, and as long as the prediction accuracy is greater than 50%, and the packet loss index decreasing, the same as we can see as we see before in the previous in the Fetri topology, the previous infatuated topology. But in our paper, we describe more simulation results with different network parameters, both for Fetri and symmetric dragonfly. So we can see it or read it in our paper. So this work has applied a proven theory for using a prediction algorithm to achieve a better network performance than standard ECMP, and calculate the lower bound corresponding to the network topology. And the simulation results demonstrated the correctness of the lower bound and the different correlation between network topology feature. As you can see for Fetri, the lower bound depends on its size. And for Dragonfly, the lower bound is a constant and does not depend on any topology feature. And also this work could lead to network research community to develop a novel load prediction algorithm with accuracy above the lower bound to ensure that they will perform better than the standard ECMP. Thank you for watching.
Okay. Thank you for your presentation. Now we have time for a few questions, so please either open your mic or write on the chat. In the meantime, maybe I can ask a question to the speaker. And in your presentation, you showed two specific topologies. So I'm wondering how easy is it to extend your results to other newer topologies? So how much do you feel the two topologies you have chosen are representative of what you find on the field, and how much is it expensive to extend your results to other topologies? Hello?
Posti, Ron, are you there? Hello?
Yeah, I see he wrote in the chat, but now we cannot hear you.
Ron, now we hear some...
Could you hear me now?
Yes.
Okay. So hello. So for your question, I think it's hard to try to extend this proof to other topologies. as you can see in my proof, that we choose Dragon. We try to prove our lower bounds on a global Dragonfly topology, and it was hard, and we don't see any possibility to find a lower bound for Dragonfly topology, and because of that, we use a symmetric Dragonfly, and because it was easy to show their lower bound, and so for a question, I don't think it will be a cheap trying to extend this proof.
Thank you. And do you think your choice of topology is general enough to be applied to a wide setting of what you find in field, or do you think that some additional work is needed to have results representative of topologies that you find?
It depends on the case. It depends on the case, because with FETRI, I think it is very good. I think the overrun is very good. It will be hard to try to find prediction accuracy that meet this lower bound in large scale networks, because the lower bound is k minus 2 divided by k, and as long as the k is growth, the accuracy should be higher. Okay. In Dragonfly topology, I think in symmetric Dragonfly topology, I think it not meets any realistic topology.
Okay, thank you very much. And I don't see any other questions. So please, if you have other questions, we have just 1 minute for one quick question. Otherwise, we can thank our speaker. So thank you, Mr. Posti. And now we can, thank you. And now we can move to the second talk of this session, failure simulation in software-defined networks with differential link availability. I think there is Dr. Luisa Jorge here, who is available for answering your question. And now I'm about to share the prepared video.
Hello, I will be talking about failure simulation link availability. I'm Luisa Jorge from IPB. My co-authors are Paul Melo, who will also present later, and Teresa Gomes from the University of Coimbra. And this work was done in the project edited by
Giacomo, it's very low.
this work. I will start by presenting the motivation, followed
The
by
volume.
the approach. And I will then present some results, finishing with concluding remarks and future work. The motivation of this work is, as we know, SDN reliability depends on existing connectivity between control nodes and their controllers. However, while link availability could matter for controller placement, this is usually ignored in most placement approaches. And link availability is even more relevant if a network is built with different availability connections by design, using something like
Giacomo, can you increase the volume?
We wanted to verify if differential link availability affects network reliability with a two-step method. To test the approach proposed, we adapt a set of controller placement IOP models, which try to generate controller placement taking into account different availability levels in edges. After this, We create a discrete event call simulator to verify whether
Sorry
the
to
placement would yield better results than
Don't he, Giacomo, you are muted.
Can you hear now?
No.
Responses can be applied to multiple placement approaches, since it isolates the
Let me try increasing. Even more.
This work was done in a project headed by Ines Quinta.
How is it now?
This work, I will start by presenting the
Later.
introduction, followed by the simulational approach. And I will then present some results, finishing with concluding remarks and future work. The motivation of this work is, as we know, SDN reliability depends on existing connectivity between control nodes and their controllers. However, while link availability could matter for controller placement, this is usually ignored in most placement approaches. And link availability is even more relevant if a network is built with different availability connections by design, using something like a spine. We wanted to verify if differential link availability affects network reliability with a two-step method. To test the approach proposed, we adapt a set of controller placement IOP models, which try to generate controller placement taking into account
Giacomo,
levels in edges.
maybe Luisa Jorge wants to
After this,
show the slides, sharing the slides.
Okay.
I don't know, but
Better result than a placement not using this information.
Luisa, would you like to share your slide?
We don't have it here, but the sound will improve in a few moments.
Ah, okay, okay.
Okay, so I have to share again.
Yes. Sorry.
Otherwise, we can show the video and you can talk on the video if you want.
Link availability. And with visual for its study due to its inherent flexibility
Giacomo, you are not sharing the video.
by design.
Yeah, a moment. Okay.
Something like a spine. We wanted to verify if differential link availability affects network reliability with a two-step method. To test the approach proposed, we adapt a set of controller placement IOP models, which try to generate controller placement taking into account different availability levels in edges. After this, we create a discrete event fault simulator to verify whether this placement would yield better results than a placement not using this information. This process can be applied to multiple placement approaches, since it isolates the controller placement stage from the sequence fault simulation stage. Reliability in networks has been frequently studied using analytical models, but simulation can be justified for its study due to its inherent flexibility, allowing the creation of models with customization capabilities harder to model with simple analytical models. These include multiple networks and edge characteristics, including multiple reliability levels of nonlinear reliability for some edges. Also, multiple fault models can be integrated, like changes on failure rate and duration and sequential failure and geographical correlated failure. And while specific analytic models can be developed to support each of these characteristics, it will be harder to create a general analytical model able to encompass all of them. The first step is the controller placement. in which we applied strategies in differential link availability networks using linear programming, adapting work from Bizarre, Thomas Mashuk, and Keller from 2016. We were particularly interested in mechanisms where we have redundant paths linking controller and controlled nodes. The controller placement tries to provide controller placement maximizing reliability, placing K controllers on the network when the availability profile of the links is known. We show here two styles tested. The first one, we have the joint paths for the same controller, using here high availability links for the main path and accepting that backup path may use less reliable links. The second one, we have paths to different controllers, a variation of the previous model, allowing the paths to be directed to different controller replicants. Again, the primary path use only high availability links, but the backup path not always. We now present the simulator structure. An application was developed in Omnet++, able to load the network, rotating the reliability information, a set of links with a different availability rating, and a set of SDN network controllers. It is created via 4 custom-built simple modules. The loader is responsible for loading the network with reliability annotations and an additional file containing the controller placement and create an Omnet network layer model. The database, which supports internal network model and exchange information regarding link faults and path failures, updating the Omnet network layer. And the base generator, which generates faults communicating with the database to update internal network information. And the simple node is used to represent each switch in the DRCN network. These simple modules are in turn integrated in the complex module fault generator, which, as required by Omnet, is integrated in a network for a dual simulation. The simulator structure allows for defining the different components, for instance, specializing the base generator with another one that allows for different kinds of faults, and isolating the fault generator from the network loader allows for supporting several networks and even new network formats without the needing to change the simulator.
A set of input variables is defined on simulator to allow for run configuration. We show here just a few of them: the ratio between high and low availability links, the interval between faults, the duration of each fault. Besides the input variables, additional customization may be achieved via network file generator, for instance, allowing for different reliability profiles on the same network and different numbers of controllers. The set of output variables relate mostly to disconnection, the expected time fraction per switch, per link, and per network for each switch in terms of each controller switch path, and seeing the input faults will translate into switch disconnection. Further output variables can be added later by creating variations on the database model. The simulator was used with two SND lib network topologies: Germany 50 with 50 nodes and 88 edges, and Polska 50 nodes and 18 edges. We used 20 different high availability spanning trees or spines for the Germany 50 network and 9 different spines for the Polska network. We also created for each topology a variation where all links share the same availability to have a baseline for comparison. For each of the network spine pairs, solutions to the controller placement problem were created for a single path for the controller, for the joint paths to a single controller per node, and for the joint paths to different controllers with unit link costs. The problems were solved using Cplex for a total number of K controllers ranging from 1 to 9. Such a high number of controllers is particularly excessive for small networks like Polska, but was used for regularity. All the placements were run twice, once using unit link costs, hop count, and the other using geographical distance count. Then faults were simulated considering the differential availability for the spine links. We tried various combinations of input variables and verifications, which meant that each typical network spine placement was run 600 times As you can see, we got a lot of results. In fact, too many results to present here in full. However, integrate analysis allows us to state some preliminary findings. We'll illustrate a subset of results with some graphs, focusing only in simultaneous failures, switch disconnection. So, in terms of results, do they show that we should consider differential linkability when placing controllers? As seen in the figure, deciding to consider or not differential availability when placing controllers matters for both network studies, but results depend on how much the availability differs. We use ratio spine as a relation between high availability spine links and the rest, and when there is a spine in the network, ratio spine greater than 4, the probability of disconnection by faults is always lower in the controller's place, taking it into account. This advantage further increases for higher values of ratio spine. Conversely, when forcing one path on link with no availability advantage, there is ratio spine equals 1, there is increased disconnection. And is it better to use the joint path to different controllers or two disjoint paths to the same controller? We have slightly different results by network. So here we show Germany. In Germany, the disconnection rate is lower when using two separate controllers than when using two disjoint paths to the same controller. We can notice a marginal exception in the Germany 50 network when using only two controllers. In this case, using two different controllers is worse than two paths to the same controller. However, in the Polska network, the results are not exactly the same. While here different controllers is always better than two paths to the same controller, and while more controllers in the network generally imply less change of disconnection due to faults, a possible exception occurs when the number of controllers is very large in this small network. We have only 15 nodes, and we are proposing 8 or 9 controllers, and we see that that's maybe really too much, which implies that maybe a point where too many controllers on a small network decrease viability. We explore different configurations of high availability links, different spines. Do the results show differences between them? Well, yes. There is some impact of the choice of specific high availability links, that is, the usage of particular spines. However, this varies strongly with the number of controllers, so no pattern can be discerned from results, and this is indeed something we need to look into in future work. And finally, a simple confirmation of what we expected to see, just to see that the simulation is not giving only nonsense results. We plotted variability versus failure duration and frequency, and as expected, the probability of disconnection from fault always increases when increasing duration and frequency of faults. You can, however, notice in the paper that the values of delay between faults and duration of these faults are intentionally kept small and near each other. These values were selected so we could find simultaneous failures without having to run rare event simulations, for which Omniat is not a great solution. However, even if that choice made the failure rate extremely high, it should not distort too much the insights gained from this simulation. And so, in summary, we present the simulation approach to validate the placement of controllers in an SDN network with different availability links. The results show that taking differential availability into consideration is useful, particularly for large availability differences among links. And, however, the advantage is influenced by the actual high availability links present, and no a priori relation was discernible from the results. For some limitation of this study, it does not consider the effect of stressing the network, nor the scalability of the analysis. Further work is required in this area, and also to that in the area of complex fault and variability pattern, therefore using the flexibility granted by the simulation approach. We finish by presenting here the references, but you can check them also in the paper. And this is all. Thank you for your time. And do you have any questions you want to pose?
Thank you for your presentation, and we have time for a couple of questions. So please, from the audience, if there are any questions, please use chat or just open your mic. Perhaps I can break the ice by asking you if you can please comment on the problem that when you have multiple controllers, you will also have some coordination overhead among the multiple controllers. So how do you think these overhead impacts on your results?
Yeah, it's true. And in fact, we tried with too many controllers for any network to be actually useful because of coordination effects. However, we're trying to see if there was some sort of regularity. We didn't try to check the particular effects of inter-controller coordination traffic on the network.
I have a question. Okay, you mentioned that you have not considered yet traffic effects, but do you expect to, for instance, that you will have some any change about the behavior if you are considering one specific communication protocol between controllers and devices or another? Do you think this can impact on the results?
To be honest, we don't expect that to happen. However, it was something we didn't do, so we consider that was relevant to present.
Okay, thank you.
Okay, if we have no other questions, so I would like to thank the speakers, and so thank you, and move to the next paper. The next paper is Constrained Policy Optimization for Load Balancing, and I think we have here Tran Anh Quang Pham, who is going to answer your questions. Let me share the presentation. Let me share the presentation.
Hello everybody, my name is Quang, and today I would like to present our work conducted in Huawei Research Center in France. In this work, we use the reverse constraint policy optimizations to solve the load balancing problem. Okay, and here is the outline of my presentation today. First, I would like to introduce about centralized traffic engineering, the use case in our work, and then we consider this. We describe the system model, and we formulate the problem using the constraint MDP and solve it using the reverse constraint policy optimizations. We do some simulations on the SD1 topology use case, SD1 use case, and then based on the simulation result, we go to the conclusion. So let's go to the centralized traffic engineering. In centralized traffic engineering, we have a central controller, which used to in charge of collecting network statistics, compute the path, and the split ratio. The split ratio is usually computed using the optimization approach for now. It means but here in our work, we want to replace using the reinforcement learning. In other words, that we want to use the reinforcement learning to compute the split ratio for every turn node in the network. And why is reinforcement learning? In fact, the load balancing is a good use case for reinforcement learning because the system model is not explicit. For example, the traffic patterns are difficult to characterize, and the impact of routing decisions on the KPI or KQI is difficult to anticipate. And we also had the promising results in the centralized cases. In 2018, RealNet paper, which adopt the centralized critic approach and do the offline training for the load balancing to solve the load balancing problem. The MLU, the maximum link utilizations, enhanced by 30%. And we also reduce the link delay and latency by 40%. If we put this for the offline training, if we want to do online training, we have to pay attention to the safety because the reinforcement learning agent during the exploration phase, they can violate the constraint and lead to the disaster in the network. Okay, so here I will describe the system model. So we consider the control plane. In the control plane, we have the load balancing agents. We have the network topology at the input, and also the tone of traffic and end-to-end delay at the input. And the agent will compute the target split ratio and send it to the data plane. We consider the time loss based system, where we have the DKT is the delay of tunnel K at time T. The SKPT is the target split ratio of tunnel K on path P at time T, and SKT is the traffic of tunnel K at time T. And they can consider as the reward, the action, and state respectively for in case of the in the view of the reinforcement learning agents. And because the tunnel K can be forwarded, the traffic of tunnel K can be forwarded over the different path. So the delay of the tunnel K actually is the maximum delay of the tunnel K on different path. And in fact, the link capacity constraint can be considered implicitly using the learn queue reward proposed in another paper. We get it. We get inspired from another paper, or we can consider it explicitly using the RCPO. And when the links become congested, so we use the maximum fair allocations to allocate the bandwidth for flow traversing that link. So that means we have some rejection there when we have the congestions. And the objective here is to minimize the delay in the network. The problem is that one way to minimize the delay is that we can minimize delay by rejecting all the traffic in the network. However, we have to avoid that case because we also want to forward the traffic from the source to the destination. So the learn queue here will have the two terms. The first one is related to the delay, and the second one to the admission. For the admission, it is the ratio between the admitted traffic over the total traffic. When we have congestions, that admission ratio will be less than 1. With the congestion, this admission rate will be equal to 1. In the RCPO, we consider the constraint explicitly. We put it into the reward and adjust the contribution of the constraint violation to the reward using the Lagrange multiplier. Okay. For the environment, we use for communication between the environment and the agent, we use the OpenAI Gym platform. In the environment, we use the simplified environment, which is adopt the MM1 delay model to calculate delay using based on the traffic and the split ratio, of course. However, this is not the packet level simulator. But we see that it's possible to extend the current environment to a packet level simulator using the work from TU Berlin. The idea we use the MM1 is because we want to shorten the training phase. The MM1 delay model is simple. Delay model will come with some assumptions. First, we assume that we have the Markovian arrival process, we have the Markovian service process, and we have one server. With these assumptions, we have the delay of the link can be computed as the packet over the remaining capacity of the link, plus with the propagation delay. Okay, so here I show you in this slide that we can formulate the problem as the constraint Markovian decision process. So let's talk about the constraint Markovian decision process first. The constraint Markovian decision process is an extension of the MDP. It also have the stay, action, transition, and reverse at the MDP. But we have another, in addition, we have the penalty based on this current state and the actions. And the constraint, it defines as the discounted penalty. Okay, and the discounted penalty from the current state to the final state. And the objective here is to maximize the expectation of the discounted reward subject to the constraint. The expectation of the constraint should be less than or equal to some given threshold alpha, and the threshold alpha indicate the hardness of the constraint. The smaller alpha here we push the Asian learner safer policy, but far from optimal policy, like we see here, longer path. If we have the higher value of alpha, for example, alpha equal to 0.5, we have the shorter path, but a risky path also. We can remove the constraint here using the Lagrangian relaxations. So by doing that, we'll have the revised reward, okay, with the penalty here. When we have the new reward, we have the new value function. We also have the Lagrangian functions, which we can get the gradient on of it, and then based on that we can update the actor and the Lagrangians. The reverse constraint policy automation actually is based on the actor critic framework, in which we will update the critic using the temporal difference, and then based on that we can update the actor. When we finish one episode, we can update the Lagrangian multiplier. For the benchmark, we deploy the NLP-based approach. We use the NLP-based approach, non-linear programming. So we also have the objective functions to minimize the delay. We have the MM1 link delay as the non-linear constraint. We have the capacity constraint, and we have the delay, end-to-end delay constraint here. Because we have the non-linear constraint, we have the non-linear programming, and we use the skip to solve this non-linear programming. For the simulation, we consider the SD1 scenario where we have 103 spokes, where each spoke connect to the hub using the internet or MPLS technology. And we had the 6 tunnels, 3 from hubs to spoke and 3 from spoke to hub. And every tunnel had a diagonal traffic pattern, and we had no background traffic. We considered 4 algorithms. The learn queue with delta 0.1 and the learn queue with delta 0.9. 0.1 means that we prefer the traffic admission, and 0.9 mean we prefer the low delay. We also consider the RCPO and also the NLP approach, the model-based approach. For the reinforcement learning approach, we have the conversions after 100,000 time step. I will show here for both the actor loss and critic loss. And for the network metrics, the learn queue 0.9, which prefer the delay, will tend to reject the traffic to obtain the lower delay. Meanwhile, the learn queue with 0.1 try to admit all the traffic but create some spike here in the delay. The RCPO is balanced between them. They obtain the very low delay comparable with the optimal delay. Meanwhile, admit 100% of traffic. So the conclusions here, the RCPO is able to avoid the constraint violations after being trained. And its performance is comparable to optimal solutions. We also, for this filter work, we can extend our environment using the packet level simulations. Thank you for your attention and question and answer.
Thank you for your presentation. And I would like to welcome the questions from the audience. Are there any questions? So maybe I can ask a first question to the speaker. And you have used machine learning, so of course there is a significant training part. And have you evaluated how frequently you have to retrain your model? So what is the assumption that you are doing on the environment that allows you to reuse your trained model?
From experience, from our experience, so the SD1 network will not change, frequently, because this is the network for the enterprises. We don't have a lot of size in the network, and it's quite stable. So that means we don't have to train or retrain it very frequently. Maybe every 1 hour or every 3 hours, so we give the new configuration to the network, so we don't have to do it very frequently. But actually, to extend it work to all the network, we have to consider another things, like we have a model-based AI to adapt to the network directly, so you can use the online training. This is our future work. Yeah.
Thank you.
I have a question. Yes. What in the simulations you used traffic that was I think in one of your last slides was the behavior, like oscillating behavior on the links. How did you produce that traffic? Is it given? You assume that some application is producing the traffic?
Yes, thank you for your question. So, in fact, we generate it using the diurnal pattern, based on diurnal pattern, which is actually in practical. So we also see that kind of pattern of traffic in the real world. So we just try to mimic that in our simulation. We don't get directly, okay, but we follow the pattern from the practical environment. Yeah.
Okay, thank you.
Thank you. Are there any other questions from the audience? Please use your chat or open your mic. No other questions. Okay, so thank you to the speaker. And we can move to the last paper of this session, compositional model checking of an SDN platform. And I think that the speaker, Dr. Abdul Mahit Norin from the University of Rennes and INRIA, is available for answering your questions. So let me open the presentation.
Hello everyone, I'm Abdul Majid, PhD student of University of Rennes 1, working in India labs with Hervé Merchant, Lojan Shampur from the same lab, and working along with Ding Tai Bui from Nokia Bell Labs. In our work, we are focusing on the formal verification of system design, in particular computational reasoning applied to the formal verification of software-defined networking. We are interested in the automated procedure to verify the correctness of a distributed system with respect to its design specification. In particular, an SDN platform is a highly distributed system in nature. It contains several entities, and overall it is designed to meet certain specifications. Specification can be like data privacy property, connectivity property between various groups of devices. Even one can express more specification, depends on his needs or her needs. We are using formal verification, a model checking procedure, to verify the correctness of software-defined system with respect to the required specification. As most of the SDN platforms, our SDN platform consists of 3 layers, namely management plane, a control plane, and a data plane. The management plane are formed by entities called managers. Each manager has the role of interfacing with the user and of converting the user's intent into high-level network policies. The control plane consists of entities called controllers, which have the role of converting managers' high-level network policies into fine-grained network rules and of enforcing those rules onto the data plane. The data plane consists of network elements embodied in the selected platform as open virtuous switches, or simply OVS. These OVSs are open source, open flow switches controlled by SDN controllers. The data plane also include end users devices which are connected to the OVSs. The main formal verification procedure is to model the system with automata, which I will come to later, and expressing the required specification as a set of temporal properties using linear temporal logic, or simply LTL. Both automata and the required properties or specification are provided to the verification tool called as SPIN for simple Promila interpreter, which check whether the system satisfies the verification or not. If it is not satisfying, it provides the counter example, which explains that where exactly the model not satisfying the specification. The distributed SDN system is modeled as a set of automata, and there is an automata to model the behavior of each component, such as manager, controller, switches, and devices. As per time constraints, I cannot go through the detail of each automaton, but you could have the detailed description of the automata by accessing to the documents provided at the open access link at the end of this presentation. In our modernization, any pair of automata communicate among them via bounded FI FOQs, provided the SDN architecture had connection between them.
Giacomo, sorry, I muted you, so the
devices
video
not belonging to a same group or vSpaces cannot exchange messages. vSpace is nothing but the cluster of devices. And the specification phi C represents the connectivity property, which express the STL system will allow two devices from a same group eventually can exchange messages. And this formal verification scheme, it is not the, of course, it's not the only way to verify the system correctness with respect to specification, but it's one of the way. And this formal verification studies actually exist in the literature for more than 30 years. In the process of verification, modeling the system, it needs the ability to describe the system in more abstract way. So the challenges here is naturally finding an appropriate model to describe the system, as well as finding an appropriate language to express the required specification. The main problem often encountered in this formal verification scheme is the state space explosion, which is actually kind of capturing the out of memory issue. There are various techniques available to encounter such a state space explosion. We particularly using a divide and conquer technique using the modularity nature of the systems. Simply, we can say compositional reasoning technique. We will describe more about this compositional reasoning technique in the following slide. The main outcome of compositional reasoning is summed up here by the following theorem. If an automata A1 guarantees the specification phi2 under the assumption of phi1, and automata A2 guarantees the specification phi3 under the assumption of phi2, then the overall composition of automata A1 and A2 working together guarantees the specification phi3 under the assumption of phi1. Thus, to verify that this distributed system containing automata A1 and A2 satisfy phi3 under the assumption phi1, we separately verify the above two predicates. This allows for avoiding the state space explosion, as we are dealing with much simpler system. Of course, the main challenge here is to find the intermediate specification or formula of phi2. However, there are techniques to automatically compute such intermediate specifications. We apply the compositional reasoning to our SDN platform by first splitting the management plane and the control plane from the data plane. This is the first verification scheme. We call them as CR method 1. The second verification scheme, we further split the management plane and control plane. This we call as CR method 2. We performed our proposed verification scheme with the personal laptop, which has Intel i7 processor and 16 GB RAM. In the table, we can notice that the monolithic approach failed to finish the verification scheme for more than 3 switches. When applying the compositional reasoning, CR method 1 and CR method 2, it can verify up to 5 switches and up to 3 domains. The compositional reasoning method 2 performs even better as we increase the number of domains, especially in the 3 domain cases here. The CPU time and the memory usage by the CR method 2 is significantly less compared to the CR method 1. During our experiment phase, we discovered some failures related to device mobility, which is again somewhat involved specification. We also made a note about this failure in the paper. Anyway, So our next step is to perform the supervisor synthesis scheme to avoid such failures. We submitted a theoretical paper regarding this framework, this compositional reasoning of SDN distributed system for more involved specification of SDN. We are currently working on to implement the proposed theoretical compositional synthesis of SDN using the synthesis tools like Reax, Heptagon, and BZR. So this synthesis scheme is actually like you have a supervisor for the local entity of an SDN, such that it work along with the local automata A1, such that it limits its behavior, such that it satisfies the local specification fee, so that like each automata model of the SDN component is supervised by such an supervisor, so that we can globally infer the global specification which we want from the SDN system. As I told earlier, that we provided the detailed model of SDN component as a automata, and also we have the spin code which we use for our experimental purposes are provided in this open access, public access link. Thanks for the attention. Now QA session. Thank you.
Hello. Hello. Thank you for this very informative speech. And we have time for a couple of questions. So please, from the audience, a couple of questions. I would like just to ask you more of a curiosity than on your general kind of work, you know, because this is not a topic that is that we see often in our conferences. And my question is, do you think that this formal verification approach can be applied to the intent-based networking model that is something which is mainstream now for controlling multiple SDN switches?
Actually, so in the literature survey when we did this, actually there is one paper called Veriflow method. What they actually do is actually it's not doing for the offline verification, they do the online verification. In that online verification, what they perform is actually whenever the intents changes or like a network update changes, it's actually checks that like if this changes happens, what is the like near future effect, and then they actually propose the real-time solution. I mean, of course it's performed better for some situation, it not performed other situation, but they do prefer the such I mean they actually implemented such a thing in open flow switches. The paper title is actually Veriflow. It's okay, I should actually check in my laptop, but okay, you can check the in online. So it's Veriflow of open software defined networking. It's actually a real-time usage of formal verification for the real intent changes, that is the live update of intent in your real system. There is such a literature in the literature. Yes.
Thank you. Any other questions? No other questions from the audience? Yes, Professor Meyer.
No, I actually don't have any question from my side this time, but I wanted just to appear for announce the coffee break. But first, please.
Okay, so if we don't have any other questions, or if you prefer to have your questions offline, we can have the coffee break here. So thank you for attending this software-defined networking session of the DRCN, and meet you in
half an hour.
Half an hour, yeah. We start at 4 p.m. With the next session. So have a nice break.
Thank you. Enjoy your coffee.